Selecting the right design pattern for component-based systems by Peter Doe. Design patterns are one of the most practical tools software engineers use to solve recurring design problems. As software systems grow larger, the way components interact becomes increasingly important. Poor design decisions early on can lead to tightly coupled code, duplicated logic, and systems that are difficult to extend or maintain. In this presentation, I'll focus on how software engineers can choose the right design pattern for a given problem instead of simply memorizing common patterns. I'll use Factory, Strategy, and Observer as examples because they each solve a fundamentally different category of design problem. Factory addresses object creation complexity, Strategy addresses behavioral variability, and Observer addresses event-driven communication between components. Together, they cover a broad cross-section of the design challenges that commonly arise in component-based systems, and demonstrate the kinds of trade-offs engineers must reason through when making architecture decisions. Design patterns matter because they provide proven solutions to common design challenges. In software engineering, component interaction is critical because components often need to evolve independently over time. A well-chosen design pattern helps reduce coupling, improve extensibility, and make responsibilities clearer. This directly connects to software engineering concepts like maintainability, testability, and long-term system evolution. Instead of rewriting large parts of a system every time a new feature is introduced, patterns help isolate change. This is especially valuable in component-based systems where multiple modules interact through clearly defined responsibilities and interfaces. Another reason design patterns matter is communication within engineering teams. When a developer says a component uses the strategy pattern, other engineers immediately understand the structure and expected responsibilities. This shared vocabulary helps reduce onboarding time and helps teams reason about architecture decisions faster. In larger projects, this common language becomes just as valuable as the code organization itself. The factory pattern is most useful when object creation logic becomes complex or variable. Rather than having the client component directly create objects, a factory centralizes the creation process and hides the implementation details. A practical example is a payment system that supports Stripe, PayPal, and Apple Pay. Without a factory, the checkout component might contain multiple conditionals that instantiate different payment processors. With a factory, the checkout component simply requests a payment processor and the factory returns the correct implementation. This improves modularity and makes adding a new provider much easier without modifying the checkout logic. Another advantage of the factory pattern is that it supports future scalability. If the business later decides to support cryptocurrency payments or bank transfers, the checkout flow remains unchanged because only the factory logic needs to expand. This separation protects the client component from frequent business changes and helps isolate risk when introducing new integrations. The trade-off is that factory introduces an extra abstraction layer, so it should be used when object creation complexity is expected to grow rather than for trivial cases. The strategy pattern is ideal when a system needs to support multiple interchangeable behaviors. Instead of embedding logic inside a single component, behaviors are separated into strategy classes that follow a common interface. For example, consider a shipping calculator in an e-commerce platform. The system may need different strategies for cheapest shipping, fastest shipping, or balanced shipping. By using the strategy pattern, the checkout component can switch behaviors dynamically without changing its own code. This improves extensibility and keeps each algorithm isolated, which also makes testing easier and supports future growth. Strategy is also powerful because it improves testability. Each shipping strategy can be tested independently without needing the full checkout component. This makes regression testing simpler and supports continuous delivery workflows. The main trade-off is that too many small strategies can make the codebase feel fragmented, so engineers should group behaviors thoughtfully and avoid creating separate strategies for logic that rarely changes. The observer pattern is designed for event-driven communication between components. It allows one component, often called the subject, to notify multiple dependent components whenever a state change occurs. A common software engineering example is an order system. When an order is shipped, multiple components may need updates. The email notification service, the analytics dashboard, the inventory tracker, and the shipping service. Instead of hard-coding these dependencies into one component, the observer pattern allows subscribers to react independently. This creates a loosely coupled architecture that is easier to extend as the number of dependent services grow. Observer also maps naturally to modern event-driven systems and microservice architectures. In distributed systems, an event such as order shipped may trigger several downstream services asynchronously. Using the observer mindset helps engineers design systems where components remain independent and can be scaled separately. However, one risk is debugging complexity, since event chains can make it harder to trace why a downstream action occurred. Choosing the right pattern is ultimately a software engineering judgment problem. The key question is not which pattern is popular, but rather, what design problem am I trying to solve? Good design starts with identifying where change is most likely to occur in the system. If the challenge is object creation complexity, factory is usually a strong fit. If the challenge is changing algorithms or runtime behavior, strategy is often the best. If the system requires event-based updates across multiple components, observer is the natural choice. Engineers must also weigh trade-offs such as simplicity, extensibility, readability, and maintenance cost. A useful rule is to choose the simplest pattern that solves today's recurring problem while still allowing reasonable future growth. A pattern should address an actual recurring design challenge rather than be introduced solely because it is a recognized best practice. Pause for a moment and think about this design problem. Imagine you are building a notification system that must send alerts to email, SMS, and Slack whenever an order ships. Which design pattern would best support this requirement, and why? The most appropriate answer is usually observer, because multiple independent services need to react to the same event. The key takeaway is that design patterns are not isolated textbook ideas. They serve as structured ways to evaluate how components should collaborate as systems evolve. It is also worth thinking about why factory or strategy would be weaker choices here. Factory focuses on creation, and strategy focuses on interchangeable algorithms. But this problem is fundamentally about one event notifying multiple independent components. That reasoning process is what makes pattern selection a software engineering skill rather than a memorization. Now, let's apply these ideas to a real-world checkout system. A poorly designed checkout system flow often starts as a large conditional chain that handles payment methods, shipping options, and notifications all in one place. This quickly becomes difficult to maintain because every new feature increases the complexity of the same component. A better design might combine factory for payment creation, strategy for shipping calculation, and observer for order completion notifications. This allows each responsibility to evolve independently. For example, adding a new shipping method should not require changes to payment logic, and notification services should remain separate from checkout processing. However, software engineers must also recognize the risk of over-engineering. Adding too many abstractions too early can make the code harder to understand than the original problem. Patterns should improve clarity and flexibility, not introduce complexity for its own sake. The goal is maintainability, not complexity introduced without clear value. Now, beyond the examples I gave, to put things into perspective, these design patterns are not just theoretical concepts we learn in class. They are actively used in real systems at some of the largest technology companies in the world. For example, Netflix demonstrates the observer pattern extremely well. When a user presses play on a video, that single event can trigger multiple independent systems at once, such as analytics tracking, recommendation updates, playback monitoring, and user engagement logging. Each service reacts independently without being tightly coupled. Amazon is a great example of the strategy pattern. Their systems frequently need to switch between different recommendation, pricing, or shipping algorithms depending on the customer behavior, business priorities, or delivery constraints. The surrounding system stays the same while the algorithm changes dynamically. Google often reflects the factory pattern through dependency injection frameworks, where services and companies are created automatically without the client needing to know the exact implementation details. These real-world examples show that the same software design pressures we study in class directly scale into industry systems. The most important takeaway is that design patterns should be chosen based on system needs, not because they are well known. Good software engineering prioritizes long-term adaptability, readable abstractions, and well-defined component boundaries. Best practices include starting with the simplest design that solves the problem, using UML or component diagrams to reason about interactions, and introducing patterns only when recurring design pressure appears. When used thoughtfully, patterns help teams create systems that are easier to evolve, test, and reason about as requirements grow over time. A good rule of thumb is to wait until design pressure appears at least twice before introducing a formal pattern. This keeps the architecture grounded in actual needs instead of speculative future requirements. The best software engineers use patterns as tools for reasoning, communication, and maintainability rather than rigid templates.